Hello. So in this lecture, we are going to study phasor and its diagram. You can find the application of this phasor in so many different chapters of physics as well as engineering, electrical engineering, electronics engineering as well. You can find its application in simple harmonic motion, where complete simple harmonic motion is basically a sinusoidal wave. You will also find some application in waves chapter also, and you will find application so much in electrical engineering where uh, you will be dealing different circuits in which RMS and which sinusoidal current, AC current will be there. So AC voltage, AC current, phase difference, power, so many calculations can be done using this phasor. So this is one of very important chapter if you want to understand electrical engineering in detail. It's a basic of it, and for students of physics as well, it's very important. So first, let us understand what is phasor. Phase it is made up of two words. This phasor is made up of two words. That is phase plus vector, and this phase you may be recalling that it is from anything sinusoidal function is there. Suppose a is y is equal to a sine omega t sine omega t plus phi sine omega t plus phi. So here you can write a as amplitude. This complete whatever this is inside it. This is known as phase. Omega here is angular frequency. Angular frequency. Phi is the phase constant or initial phase. Initial phase. So this phi naught better you write it for initial phase. So this complete phase you can say this phase as a function of time. This will be a function of time. So whatever this is inside this time, omega t plus phi naught, this is known as phase. And we are going to study about this vector. We are going to represent this phase in terms of vector, or you can say rotating vector. So phasors are also known as rotating vectors. Rotating vectors. Example of the phasor you can see in this diagram how we can represent sine function, sinusoidal function in terms of phasor. So phasor definition, if you want to see, it is a phasor is basically phasor is a complex number representation of complex number representation of complex number representation of sinusoidal function. Sinusoidal function. Sinusoidal function. And here the condition is where amplitude frequency or angular frequency and initial phase are time invariant. Initial phase are time invariant. That means it does not depend upon time. This is this is a basic definition of phasor. So basically in phasor we are going to represent this sinusoidal function. Sinusoidal function, that means function of sine or cos function, both are having sinusoidal shape. And in that phasor, this we want to draw the diagram of the phasor: amplitude, frequency, and initial phase. These three quantities here: amplitude, this is frequency, angular frequency, or this is here initial phase. All three will be time invariant. That means it does not depend on time. Otherwise, we cannot draw the phasor of it. So you can see in this diagram. Let us first see one more diagram which is just below this page, which will make you more clear how this phasor is drawn. So here if you see that at 0-degree angle, this is the rotating vector. Here what we do, if suppose you want to find the phasor of this diagram, this equation, not diagram, this equation, A is equal to am sine omega t plus phi. So what you have to do, you have to first find the amplitude of this. Once you have found the amplitude, you have to draw a vector. In this red color it is drawn, this one, this vector, and you can see this vector will keep on rotating. You can see with what speed, angular speed, omega radian per second. That means the speed of this vector rotation will be same as the speed, angular frequency, and this angular speed will be same. So you can represent this here like that. So at theta equal to 0-degree, the graph will be somewhere here. Now as this vector is rotating, when it reaches 30-degree, you can mark this point here. Then again when it reaches 60-degree, you can mark this point here. When it reaches 90-degree, you can mark this point here. When it reaches 120-degree, you can mark this point here. Similarly, when it reaches 210-degree, you can mark somewhere here. 300-degree when it reaches, you can mark here. When not here, here. 330-degree, you can mark. When it reaches 330-degree, mark here. When it reaches 360-degree, you can mark. Then after again repetition will start. That means once this vector is rotating, you can draw the sine wave here. So this diagram is known as phasor diagram. Basically, this is the phasor diagram of a particular sine wave. Phasor diagram, this is how we draw. We draw a circle of radius, this amplitude, radius of this amplitude, and this will rotate with angular velocity omega radian per second, which is same as angular frequency of the SHF. Then only it will match exactly. And this theta here, it will be initial phase. Suppose here this phi naught, you can represent here this phi naught, initial phase. That means this sine does not start from 0, it will start somewhere here. Then again it will go like that, like that. If this initial phase is 0, then you can see in this diagram it has started from exactly at this position. If it will have some other phase other than 0, then you won't be getting it will to be started from 0, it will be starting from something else. So this is how we are going to draw the diagram of this phasor. So in other words, you can also say phasor is a rotating vector. And here you can say in this diagram that This, if you want to, I'll show you one of the animation how the sine wave is made. You can check here this animation. If you check this animation here, if I play this, you can see how the sine wave is made. This vector is rotating with angular speed of omega. Yes, this one. This vector is rotating. This blue color vector is rotating with angular speed omega, and with the same, which is having the same frequency as of that of the sinusoidal wave. So you can see this. A famous example of this can be of simple harmonic motion, which is shown in this diagram. Now you can check how this is exactly matching here, how this sign is developed. Now, once I stop here, now you can check this point. Now here, this point represents this point here. Now when I do this, now slowly you can see how this point, this you concentrate on this point. This point is making sign. So this point is moving here. Now you can see the projection of this amplitude on y-axis. This small line is there, this line. This is the projection of this amplitude on y-axis. And this can be seen here also. This also is a projection of this amplitude. So as you see in the next step, this projection is also increasing, decreasing according to the position of the particle. Now see, this projection is maximum. Now it will start decreasing, decreasing, decreasing. This projection is 0. Now you can check. Now at this position, it is having some projection, so increasing projection, now maximum projection. So this is all about phasor diagram, how it is drawn. Let us go back to the here. Now this projection, when you see, this projection only is a sine omega t. You can check here. This projection is a sine omega t, because I'll show you this diagram. This is theta. If this is phi, then you can see this line will be, this line is same as this line. And what is the value of this red line from this triangle? This triangle, when you find out the value of this red line, you will get a sine omega phi, omega a sine phi, and phi is the phase. This phase is changing with time. Initially it is some phi naught, say phi naught here, but it will not be constant, it will change with time. How it will change? This phi can be written as omega t plus phi naught. So this represents the SHM. That means this projection here of the amplitude, that red line, will represent the simple harmonic motion also. So this can be used for current as well, for voltage as well. Similar diagram we can make for that also. So here also you can see in this diagram, you can draw the diagram of current as well. If suppose current as a function of time, simple, you can write I naught sine omega t plus phi naught. So if you want to draw the phasor diagram, just what you have to do, you have to take the maximum value of current amplitude, you can say that is I naught. So you can draw the circle of I naught, and it is initial phase is phi naught. So somewhere here, from here you can take initial phase phi naught, and this is moving with angular velocity of omega naught. So you can represent like this. It's moving with angular velocity omega naught. And this width, this length of this arrow will be I naught. That is how you can draw the phasor of current. Suppose in same diagram you have to draw phasor of voltage to be something V naught sine omega t plus phi 1, or this phi 1 you can take as anything like minus 30 degrees suppose. So you can represent some here minus 30 degree, it will be down minus 30 degree. And this amplitude, suppose this is more than current, I am not telling that these two value will be same. They can be different also. So if it is having more value, you can voltage, you can represent little length, little bigger. This will be not, and it will be moving in some other circle, this bigger radius circle. But the omega it will be same, and this length will be V naught. So this is how they will be representing. You will be representing these two vectors here in the same phasor diagram. This will be a phasor diagram of current and voltage. Now if you see further, now we are going to study the vector algebra for this. Before that, in the starting I told you that it is complex number representation of sinusoidal wave. That means basically complex number, you know, anything, say C is a complex number. You can write C is equal to A plus IB. This is known as a rectangular form of representation of complex number. Generally in physics, since I we represent for current, what we do instead of that, we write J here, J plus B. So basically complex number can be represented in three ways. This all is a part of mathematics. So briefly I am telling you, it can be represented in three ways. One is rectangular form, rectangular, form. Another one is the same as this one, is known as only rectangular form, in which you will represent this as A plus JB. This is not of that much important. Next one is your polar form. This also is a polar form, exponent form, better you write exponent form or exponential form. That means C you will write magnitude, you will find for this magnitude will be, say M is the magnitude, e to the power j into theta, angle between them. How they are related? You can represent this complex plane. If you represent on complex plane, just like a vector only, you can write this is A B. So this is A, this is B, this is theta. Theta you can find as tan inverse of B by A, and this length of hypotenuse you can find root over A square plus B square, and this you can write as M only, which I have written here M, and this theta is here from here. And one more form is there, that is phasor. In phasor, what we do, instead of writing that big, what we do is little short we do. M angle theta. Just we reduce this format. That means it is a just short format of exponential format. Here angle is theta. M and theta already we have proved from how we are going to convert from rectangular form to this format. So this is what we are going to use phasor here, this format. Now next is vector, just like vector algebra, since phasor is also a type of rotating vector only, so all the algebra almost symmetrically you can use for phasor as well. So next we are going to study phasor algebra. So in this algebra, first thing will be addition of two phasors. Addition of two phasors. So suppose something like y1 is equal to, suppose y1 is equal to a1 sine omega t, and y2 we have to add this with something like y2 is equal to a2 sine omega t plus phi. Suppose you want to add these two. So when you add these two, since this is a vector, you can represent this. You can write in phasor format. How will you write? Y1 is equal to A1 angle 0, because here initial angle we write. Y2 you will write amplitude, A2 angle phi here you can write. And if you want to represent this phasor in phasor format, what you will do? You will just draw a circle of two circles of different radiuses. So here one will be A1, we don't know which one is greater. So let us take A2 is greater than A1. But this is having phase phi. This is will be here initial phase phi A2, and this is initial phase A1 here. Now if you want to add this vector will be nothing but it will be a rotating vector only. This vector is a rotating vector only. So these two vectors will be rotating. But every time when you find the resultant of this since it is a vector, so omega will be same. This is also rotating with omega and this is also rotating with omega. That means every time they will maintain a phase difference of phi here. So when you find the answer for this, that means just a vector addition. You can draw parallelogram here, and this resultant of this two vectors will be given by this. You can write this as a net, and this you can write as the initial phase phi naught. So you can write this y, that means y1 plus y2, that means we are just adding two sine functions. You will be getting something like a net sine omega will be same omega t. This phi naught, instead of phi it was initially phi, now we can write phi naught, which is here this one phi naught. Phi is this one initial phase of 2. And a net can be found out by using the vector method of addition of two vectors, that is root of over a1 vector plus a2 vector plus 2 into a1 a2 cos angle between these two. So angle between these two is phi That means phase difference you have to write here. Phi naught also you easily you can find if you check phi naught. So this phi naught you can write as these two vectors are there. Once again I'm drawing here this one. Another vector is this one. Addition of these two vectors is the A resultant vector here. So A resultant vector, this is A2 only, this is A1. So this line length will be nothing but A2. And let us draw one triangle here. So this is say phi naught. So this angle also, this is phi. This complete is phi, not phi naught. So this is phi. This complete it is phi. So this angle also will be phi here. So in triangle ABC, in triangle ABC you can write tan theta is equal to BC by AB. So BC you can write what? BC you can write as this length. This length that is A2 sine phi by denominator AB you can write A1 cos phi. You can write here as A1 cos phi plus not A1 cos phi, just A1. A1 will be only A1. A1 plus this length plus this length. This length is A2 cos phi. So this theta you can find like that, tan theta. So from here you can write this phi naught. This is phi naught, tan phi naught, tan phi naught and triangle ABC. So this is how we are going to find out. So this most of the application we will be finding the net amplitude only. Very rarely it is asked to find the initial phase of the resultant vector. So this is the addition. Same way you can go for subtraction also. Just like vector subtraction we do. Same thing. Only difference will be instead of plus here, subtract if you want to find subtraction. Subtraction of two phasors. Subtraction of two phasors will be nothing but already we have got this result, that is root over A1 square plus A2 square minus 2 into A1 A2 cos phi. This result already we have derived for vectors. As it is, we can use here. An initial phase will not be asked. Very rarely it is used. So most of the application will not be based on subtraction. Very rarely you will be asked to find out the initial phase in that case. Third and fourth mostly are used for finding. Most of its application will be there in the electrical circuits where AC currents will be there. Multiplication of phasors, two phasors. So two phasors you can write same like we have written last time. Y is equal to, we are using these two phasors only. Y is equal to y1 or y1 is equal to A1 sine omega t, and same y2 is equal to A2 sine omega t. So you can write this in exponent form. Y1 is equal to E1, y1 is equal to A1 e to the power j into, here angle is nothing, is let us write this as phi 1 here better, so that you can get a better result. Otherwise you will get result for a particular value. So better we will write here phi 1 and we will write here phi 2. So j into phi 1 and phi 1. Y2 you can write A2 e to the power j into phi 2. Now when you will multiply these two, that means y1 into y2, you will be getting a1 a2 multiplication, and e to the power, these two if you multiply, they are in exponents, so they will be just added, phi 1 plus phi 2. So this is how we have written for exponential form. You can convert this into phasor form as well. A1 a2 into angle of phi 1 plus phi 2. So in multiplication, when two phasors are multiplied, the amplitude will be just multiplied and the angles, that means initial phases, will be added. This is what we will be getting the result. Now next, when you divide these two phasors, division of two phasors, division of two phasors, how we are going to divide. So in same, instead of y1 to y2, we will be doing y1 by y2. You will be writing a1 e to the power j phi 1 by a2 e to the power j phi 2. Now here you will be getting a1 by a2, and e to the power, here you will get j phi 1 minus phi 2. So here this magnitude you will be getting just multiplication by division only, and instead of addition last time we did for multiplication, here you have to subtract. So this is all about phasor algebra. So these will find their application in both SHM waves and your electric circuits of current which is not DC, which is AC.